Just plot Nyquist for the given transfer function. In this case, we are going to assume a transfer function. Suppose the transfer function given is s squared by s plus 1 into s squared into s plus 2 into s plus 3. This is an open loop transfer function. You will be given open loop transfer function only to calculate Nyquist. So we now have a function. We must now find out about which region this must be evaluated. It is to be evaluated because we need a plot. So in order to get a plot, we can either manually substitute the points or directly substitute equations of lines. We must first know which region we should consider in plotting. According to Nyquist, the Nyquist region, the so-called Nyquist region is the entire half of the S-plane where the system is unstable. The entire half of the S-plane including the j omega axis. This is the j omega axis considering this is S-plane. This is the j omega axis and the entire region of the S-plane. And mind you, it must avoid poles or singularities. Here for the given transfer function, let us first plot the poles and zeros. Here 1 by s square is there, so there are two poles at origin, one pole at -2, the other one at -3. The 0 is -1. Now we have to avoid the poles or singularities. So there is a location of two poles at origin. So the Nyquist region which is passing must avoid this. So how this will avoid is, let us take a detouring region. This is called detouring path or detouring region that tours around the pole having radius sigma tending to 0, because it must only avoid the pole and everything else other than pole must be inside the region. Now this bigger semicircle is of radius capital R tending to infinity because we assumed the region, or the Nyquist assumed his region to be tending to infinity. Now this is the region about which we have to evaluate this function, this open loop transfer function. How we can do, let's see. This is an open loop transfer function given into h of s plus 1 by into s plus 3. Now let us divide this region into 4 parts. This is the first part, this is the second part, this entire bigger semicircle is third, and this is 4. Now this, let us first evaluate the first region. Substituting the points on this region in S, we will get a plot. Okay. Now instead of substituting all the points, let us substitute the equation of the line itself, s equal to j omega. So substituting s equal to j omega in the given equation, h of j omega equal to j omega plus 1 by j omega whole square, j omega plus 2 into j omega plus 2. Now this is the transfer function. In frequency response analysis, in order to plot something, we need magnitude as well as phase. Magnitude and phase are required. So now let us now calculate the magnitude equation of the above transfer function. Magnitude equation, that is nothing but mod g of j omega into h of j omega. Now a plus ib magnitude is under root a square plus b square. This is a complex plane and 1 plus j omega is there. So the magnitude for the j omega plus 1 is under root omega square plus 1. J omega whole square is omega square. J omega plus 2 is omega square plus 4 and j omega plus 3 is omega square plus 9. This is the magnitude equation. Coming to the phase equation. Phase equation is, for a plus ib, the phase is tan inverse of b by a, or the angle. In the same way here, considering j omega plus 1. For zeros, the angle will be positive, that is plus tan inverse of b by a. For poles, it will be minus tan inverse of b by a. Considering this, for j omega plus 1, since it is a pole, this j omega plus 1 is a pole, we will write it as tan inverse of omega. That is omega by 1 is omega. Now, for 1 by j omega whole square, for pole, for this is 1 by s, that is 1 by j omega. For 1 by j omega, the phase is minus 90. As you can see, this is j omega. 1 by j omega is nothing but the reverse, minus 90. Minus, suppose if there is one more pole in addition at the same point, it will be minus 90, minus 90, minus 180. If it is 1 by j omega whole power n, it will be minus 90 into n. In the same way, since it is 1 by j omega whole square and it is a pole, so it is minus 180. The next thing is minus tan inverse of omega by 2, minus tan inverse of omega by 3. This is the phase equation, this is a magnitude equation. Now, let us plot the points for different omega values. For omega magnitude and phase, firstly let us consider omega value as 0. Magnitude is infinity, substitute omega equal to 0 here, you get infinity. Phase, tan inverse of 0, if you substitute omega equal to 0, tan inverse of 0 is 0, 0, 0, minus 180 degree. If you now substitute directly infinity, what will you get? The magnitude will be, when you consider it as infinity, the magnitude will be 0. And if you take this as infinity, this is 90 minus 180 minus 90 minus 90, and you get minus 270 degree. Okay, let us assume this is phi initial, phi final. The reason for this is we have only plotted 0 and infinity, so we must know starting and ending direction. Ending direction is nothing but phi final minus phi initial. So phi final minus phi initial is nothing but minus 270 minus 180. It is minus 90 degree. Now, listen, this must be noted. Since this is negative, whenever delta phi, this is called delta phi, whenever delta phi is negative, ending direction is clockwise. If it is positive, the ending direction is anti-clockwise. This you must remember. If delta phi is negative, ending direction is clockwise. Delta phi is positive, ending direction is anti-clockwise. Now, when there is ending direction, you must know starting direction. Starting direction, the shortcut is, if pole is closer to origin, the starting direction is clockwise. If 0 is closer to origin, the starting direction is anti-clockwise. Now you see here, there is a pole at origin itself, a 0 and a pole. Mind you, you must remember, you must not consider the poles present at origin itself. You must strictly bind to the rule that it is closer and not exactly. So which is closer? It is not pole which is closer. Pole is exactly at origin. Only 0 is closer to origin. So since pole is farther from origin, 0 is closer to origin, the starting direction for this problem is anti-clockwise. Okay. Now we know the values. We know starting and ending direction. Let us try to plot this. This is a plane where you have 0, 90, 180, 270. In the same way, minus 90, minus 180, the same phase can be called minus 90 also. It means minus 270. Here, everywhere else, here the magnitude is 0. It will tend to infinity at all these points. Magnitude will be tending to infinity everywhere. At this juncture, the magnitude will be tending to infinity, and it will be 0 here. Now, you know starting direction, ending direction, and magnitude is infinity, phase is minus 180 at omega equal to 0, omega equal to infinity, magnitude 0, phase minus 270. Now, magnitude is infinity means it is infinity at all the 4 points, but the phase is minus 180, so minus 180. So from this the plot should start. Now, in which direction should it go? In this direction, in this direction. Now we have assumed that starting direction is anti-clockwise. We have got anti-clockwise direction. So it must start anti-clockwise. This is a clockwise direction. This is anti-clockwise direction. So this is starting anti-clockwise. Next, we know the ending direction is clockwise. Where it is ending at minus 270. This is a minus 270 line. It must end clockwise. This is clockwise. Clockwise. It is ending in this way. So we know the starting and ending direction. So ultimately the plot we get is in this way. Yes. So for s equal to j omega, the whichever plot you get is nothing but polar plot, and this is polar plot. And mind you, listen, we know only starting direction and ending direction. We can draw it in this way also, right? The plot can be any way. We know that it is ending at here, starting here. That's it. So whether it's correct or this is correct, we doesn't know at this point. To know, we must first know number of intersections. Number of intersection. Without knowing intersection, we can't decide which is correct. This is or this. So we must, to find out number of intersection, we must first calculate omega PC. So before getting into this, let us first assume, before getting into omega PC, let us first complete the plot. Suppose if this is the polar plot, let's think the mirror image, that is, this is only for s equal to j omega, that is only for the first part. We must calculate for second, third and fourth. For second part, it will be just a mirror image around the x-axis. So this will be the same for region 2. So this is the direction, this must be the direction, continuous direction, just mirror image. Now for entire this region of circle, bigger circle, that is for third region, this is a semicircle, right? In a complex plane, this is S plane is however complex, z equal to r e power I theta is the circle equation. Now here r e power j theta, this r, this z is nothing but is equal to r e power j theta. For the semicircle, theta varies from, for this region if you can observe, this is 90, this is minus 90. So the theta is varying from minus 90 to, from plus 90 to minus 90. So since the given transfer function has 1 by s square into s plus 2 into s plus 3, for 1 by s square or for 1 by s, for any, generally for any pole at origin, if you consider any pole at origin, if you have any pole at origin in the given transfer function, if you substitute 1 by r e power j theta there, ultimately the transfer function you get will, if you substitute r e power j theta in the same way as s equal to j omega, I am substituting s equal to r e power j theta, where theta is varying from minus pi by plus pi by 2 to minus pi by 2. So 1 by r into e power minus j theta, theta varying from plus pi by 2 to minus pi by 2. Now, since r is tending to infinity, this value will tend to 0. So ultimately you get 0. That is, this entire region contributes nothing but a single dot, or nothing but a single dot at origin itself. The magnitude you are getting is 0 here. In the same way, if you consider this fourth detouring region, here the circle will be sigma e power j theta, where theta varying from minus 90 to plus 90. As you can see in the diagram, this is minus 90, this is plus 90, it is moving from minus 90 to plus 90. So for this region, if you substitute 1 by sigma e power j theta, we are considering 1 by s because we have 1 by s here. For any 1 by s square or 1 by s power n, or for any value which is for any pole at origin, ultimately you get this only. That means you get a dot for bigger semicircle, and if you have a detouring region, you will definitely have a detouring region. If you have a detouring region, 1 by sigma e power j theta, if you substitute 1 by sigma e power minus j theta, you can convert it in this way. The theta is varying from minus 90 to plus 90. As sigma is tending to 0, 1 by sigma will tend to infinity. This infinite value will appear from minus 90 to, that means plus 90 to minus 90, because it is minus j theta minus j of minus 90 to plus 90. That means j of minus 9 plus 90 to minus 90. So from plus 90 to minus 90, you get a detouring region, that is, yes, from plus 90 to minus 90 you get a detouring region. Plot as a bigger semicircle from plus 90 to minus 90. But the plot we have is 1 by s square here. For 1 by s you get from plus 90 to minus 90. For 1 by s square, this will be the, sigma e power minus j into 2 theta you will get it. So this is 2 into minus 90 to plus 90. And since it is minus j theta, you get it as j theta plus 90 to minus 90 into 2. So ultimately you get from plus 90 to minus 90. Or I will clearly explain here. 1 by sigma e power j theta. Since it is 1 by s square, this will be square. For 1 by sigma square e power minus j theta into 2, that is e power minus 2 j theta. This however will tend to 0, tend to infinity. This e power minus 2 j theta is actually, the detouring region is varying from minus 90 to plus 90. So minus 90 to plus 90, that is e power j of plus 180 to minus 180. That is, this infinite circle will encircle from minus 180 to plus 180 to minus 180. So if we are just considering that here there is only one intersection, so if there is only one intersection, it will be this as you can see it, and this is plus 180 or minus 180. Now as we have come to the conclusion that as sigma tending to 0, 1 by sigma tends to infinity, and we get a infinitely big semicircle, circle which is going from plus 180 to minus 180. So this is the other matrix, and the direction is, this is the direction we have got from plus 180 to minus 180. Now we have to calculate the